So we've spent a fair amount of time graphing with rationals, but let's take a little break and talk about solving rational equations. It's not too much of a stretch because technically when we think about solving, it's kind of like saying maybe you've got the graph of a rational that looks something like this, and we're just finding where it intersects with a particular line, right? So that's basically all we're finding. So if you think about solving in that way, I think it helps a little bit. And that's how we thought about solving polynomials in the last unit too. So remember, there is a graphical connection that I think is super, super helpful. So let's just try solving an example. How about we try -5 over 2x, so that's got a nice rational feel to it, plus 3 over 4x is equal to -7 over 4. So our first solving problem. And we like to start by considering the domain, just like we did, in earlier parts of this unit, because domain still matters, it turns out, for solving. So maybe I'll just jot the domain at the top here. In looking at these separate fractions, I don't even need to combine them to be able to tell that the domain is going to be everything but 0. So we want to make sure that if we were to get 0 as a solution, it would be rejected because we can tell that plugging in 0 for any of those denominators, well, at least those first two, would cause us to be undefined, and that's problematic. So I'll revisit that once we find our solution. But the basic technique of solving rational equations could be thought of as find your LCD, find the least common denominator between all the fractions, and then make all denominators have the LCD. So that's going to be a good kind of mindset, because if I can get all my fractions to have the same denominator, then it's basically like we can multiply through by that LCD and it quote goes away. So just real quick to lay what I mean by that, to lay that foundation, I'm going to make a statement that's true. So would you guys agree that 5 over 7 plus 1 over 7 is 6 over 7? That's a true statement, right? Because all the denominators match. Is the truth of that statement in any way changed if I were to eliminate the denominators? So is it still true that 5 plus 1 equals 6? Yeah, still true, right? So that's going to be our technique here. We're going to get all the denominators to look the same. Then we're going to basically multiply through by that LCD to clear out the denominator, and then we'll solve what remains. So we'll walk through that together. The LCD can be a little interesting at first, but the way you want to think about an LCD is it's something that you can multiply all the current denominators to look like. Sometimes one of the denominators is the LCD, or sometimes they all have to change. So let's think through this. If we have a 2x, a 4x, and a 4, just numerically, would you guys agree 4 is something that all the denominators can be made to look like pretty readily, right? Two of them already have 4. And the denominator that has a 2 could simply be times by 2, and then it looks like 4, right? We're able to change denominators through multiplication. The other part of the LCD involves the variable. So we can see that 2 of our denominators involve the variable x, so it won't be hard to make that third denominator gain a factor of x. So the least common denominator in this example would be 4x. So now what I need to do is I need to show changing each of my denominators to look like that LCD. So I'm going to give myself a little bit more space. And this is kind of how I like to show my work. So I'm giving space so that if the fraction needs to change, I can do so. So what do I multiply 2x by to make it look like the LCD of 4x? It just needs a factor of 2. So 2 times 2x would give me 4x. We know for fractions, though, if you change them on the denominator, we need to change by the same factor in the numerator so that it's equivalent. So I haven't changed the equivalency of that fraction. It's kind of like me saying, 50 out of 100 is still the same as 1 over 2, right? They're equivalent fractions. This next fraction of 4x, it is the LCD exactly, so you don't need to change it. Some people feel a little better if they show timesing by 1 just so they don't feel like they neglected it. Feel free to do that, but if a fraction already has the LCD, no change is needed. What about this third denominator? We've got a 4, so to make it look like 4x, that's right, we're just going to times it by x, top and bottom. And because this is our first example together, I'm going to take a quick moment to rewrite and clean up. So I'm just going to simplify what we have here before I take the next step. So I'm just cleaning up, and then it's really at this stage that I knock out the denominators. As we showed a moment ago, it's still the same equation. It's still equivalent. So you could do that now, or some people maybe feel more comfortable adding these two fractions first. So I'll try that. Negative 10 over 4x plus 3 over 4x just means add the numerators because the denominators are the same. So negative 10 plus 3 is negative 7. So I get negative 7 over 4x equals negative 7 over 4x. And if it's okay with everybody here, timesing through by that LCD is what eliminates the denominator. So if you want to show it, you can, or if you're okay just saying that negative 7 equals negative 7x because the denominators are the same, that's cool too. This results in just a friendly linear equation, which I can solve by dividing both sides by negative 7. So the solution here is 1 equals x, or x is 1. So the solution of x equals 1, before I box it off and walk away and call it a day, ought to be compared back to the domain. You may recall our domain here we had noted was everything but 0. So since I got a solution of x equals 1, I just quickly check it against the domain, and the domain is fine with a solution of 1. It won't cause any problems to plug 1 into the function. So x equals 1 is the solution here. We got one solution and the domain was fine with it. So that would be the end result for this solving problem. You guys know by now how much I love graphing to check my work, so I've actually already graphed this one, and I'll show you it on the next screen just as confirmation for what we've done. So I graphed it in Desmos, and really all I did to graph it in Desmos was I plugged in the left side as an equation, y equals this, and the right side as an equation, y equals that. And I'm looking for the x-coordinate where they intersect. And we know from our algebra work it should be 1. So let's see if we did good job. So in blue is graph the left side of the equation, in orange is graph the right side. And you can see this point of intersection is 1 comma negative 1.75. We just found a solution for x. So x equals 1 is the solution. And hey, that's what we found. So try out graphing. It's super nice to boost your confidence when you do some solving. All right, we'll do another example in the next video.